So far, we've discussed quite a lot about inertia, what it is, the system inertia around the world, and how to estimate inertia. In this section, we'll start trying to connect the dots between inertia and frequency control during large disturbances. Here we'll talk about more about the modeling of frequency control and how we can try to assess frequency stability during these large disturbances. So what is a large disturbance in a power system? So in the context of frequency control and inertia, a large disturbance, it refers to contingency events that cause material active power imbalances. They could be large generator trip, generator contingency, a loss of interconnector, an in-feed loss, a network fault that leads to the disconnection of multiple generators. So you might have a radial section of the network that has generation and you lose that. A transmission line fault that leads to a large loss of load. So again, you might have a radial connection to a load and you have a fault on that line. Or alternatively, you might have a lot of lightning in the area that manages to trip a lot of load at once. And significant network fault that can lead to the loss of distributed rooftop PV, so DER tripping. And this is something that's sort of an emerging risk that we'll talk about a bit later. Or combinations of the above, so multiple contingencies. So in this section, we're really going to focus more on the loss of generation contingencies, but the underlying concepts are equivalent for loss of load over frequency events as well. And this is what happens when we all get it wrong. So earlier this year, we had a large generator trip event. It was actually a multiple contingency that caused under frequency load shedding in the Swiss, and we, as the news stories report, there were about 100,000 homes that got blacked out. In this slide, I'll give a stylized description of how frequency control is supposed to work theoretically during a generation contingency. So to begin with, we'll start with a generation contingency, and the initial response we get is the inertial response. So as we've described before, so inertia rapidly injects energy to suppress the frequency deviation. So it's the exchange of energy from the rotating masses into the loads in response to a frequency deviation or mismatch in generation and load. In this case, there's a loss of generation. So the frequency starts to decrease and will keep on decreasing until the system collapses, if not were for primary frequency response. So primary frequency response is local active power controls that act in a proportional manner. So it's local to the generating units and they respond to frequency deviations and they're there to arrest frequency deviations. So usually things like governor speed droop controls. So here we see primary frequency control come into play, and what we see there is we see the minimum frequency point, which we call the frequency nadir. And then it usually settles at what is called a quasi-steady state settling frequency, or the QSSF. And at that point, all of the primary frequency responses, or almost all, has been deployed, and it just sits there because that's sort of the droop deviation. What you need to bring it back up is a secondary frequency response, and typically this is done by the automatic generation control system, the AGC, which sends sort of signals to generators to restore frequency back to nominal frequency, basically by upping everyone's active power outputs. So here we see the AGC take effect, or this secondary frequency response, and then finally we have sort of a tertiary response, which you could call rebalancing or redispatch. So this is where you start up new units or you change the set points on operating units which act to replace any depleted secondary frequency control resources and bring the system frequency back to within its normal operating band. This could be manual, it could also be part of the dispatch engine. So if everything works perfectly, this is what would happen, and we would avoid the upper threshold. In this case, in the Swiss, it's 48.75 Hertz. Here we see an example of an actual generator contingency in the Swiss. So this was a 160 megawatt generator trip in January of this year. And you can see the frequency starts around near 50, and then you have the event, which I've triggered at 0 seconds. And you have a rock off here of 0.26 hertz per second, or minus 0.26 hertz per second. And it drops, hits a nadir of 49.62 hertz, and then recovers to a settling frequency, and then eventually back into the normal operating band. And here you see the primary frequency response, like an aggregated primary frequency response, and you see the inertial response to begin with of all the generators, and then followed by a primary frequency response, and then a secondary frequency response to bring the frequency back up to the operating band. Here we break down the frequency response components and sort of tease out what they do and their effect they have on system frequency. So here we have a generator contingency. In this case, this is actually a real contingency as well, so 217 megawatts, and the generator inertia at the time was around 16,680 megawatt seconds and a load of 2,400 megawatts. And if all we had was inertia, this is what would happen. Inertia is there to basically retard the fall in frequency. So if inertia was lower, it would just fall faster, basically. If we had inertia and load relief, so we had some load damping, this is what we would see. So load damping, we'll discuss this in more detail later, but load relief is basically the natural sensitivity of loads to frequency deviations. So there's quite a few loads like induction motors that actually just reduce their power output when frequency gets lower. So with load relief, you don't see it collapse all the way. I mean, it's pretty bad. It goes to 48.2 hertz, so you're already in the load shedding territory, but it does stabilize. If we had load relief and just the AGC system, so this is just the automatic generation control, like a central control pinging active power outputs to different generators, then we'll get an improvement in frequency response. But you see here that still breaching the upper threshold because AGC is slow. It takes quite a few seconds to send a signal from the central operating center to the different units in the field. So if we had inertia and some load relief and now the primary frequency response, so just the generator droop, this is where we start seeing some better frequency responses. And here we see that the frequency response is limited to a reasonable nadir. However, it settles at a frequency that is below the normal operating frequency band, the NOFB. So what we really need is all of the different components put together, and that brings you back towards 50 hertz and the droop dead band. A system frequency response model, or SFR model, basically describes the aggregate behavior of system frequency in response to active power disturbances, so like a generation contingency. So you might have a disturbance here, a delta P, and just as an input to the model, you plug it in and you get some kind of frequency deviation at the end of that. So in the early days, SFR modeling was pretty simple, and it was based on some linear metrics. For example, here's the composite power frequency characteristic that Davies and the like did in Great Britain, and this is back in the 1950s, late 50s. And you can see it is a characteristic K, which is basically delta P divided by delta F. So you have a change in active power, which is disturbance. You have a change in delta F, and if you can break it down further, you have a generator component, change in generation, and then you have a load component, or a change in load. And so this was beta and alpha back in the day. So the parameter K actually represents the composite effects of an active power disturbance on the system frequency, and is measured in megawatts per hertz. So if you gave an injection of, say, 100 megawatts, and you had a megawatts per hertz of 100 megawatts per hertz, then you would get a 1 hertz change in frequency as a result. And back in the day, they were really estimated, this parameter K was really estimated using experimental tests. So they were brave enough to actually put online and generate a trip. So I know that in Great Britain, they tripped some lines to trip off generators, and Berg in Norway was tripping off generators as well back in the 70s. So system inertia is not really an explicit parameter in K, but it is actually implicitly included because K is sort of a catch-all metric. But it is quite simplistic because it's linear, and we do know that frequency doesn't behave linearly to active power changes. We've largely moved away from using simple catch-all metrics like that parameter K, and most of the modern sort of SFR models are now really developed based on expanding out the terms of the swing equation and treating the system as a single machine with a single frequency. So you often see the terms single frequency model or single mass model also being used for an SFR model. So generic structure of a SFR model is shown below, and these quantities are in megawatts and hertz. They could also be in per unit, but this is structured in sort of natural quantities. And you have here the inertia model from the swing equation, and here's all the parts that form the delta P part. So this is really just the inertia model here, and with load damping then stuck in sort of external to the inertia model. So in some models, the damping factor is included in this block, as we'll see later, but you can also include it externally through load damping as a part of the change in active power. So this is the primary frequency response, the PFR. Here's the contingency, so it could be a load or it could be a generator contingency, but just for the sake of contingency right now, it's a negative, so it'd be a generator contingency, so it's a negative active power imbalance. And here we have just a generic transfer function for demand response. So a bunch of underlying assumptions for using such a model, and here are the main ones. The model really ignores all network topology, so we're not even looking at transmission lines, substations, or anything like that. We're just lumping it all into a single node. So all generation, all loads, all just hanging off the same node. But one implication of this assumption is that if there are genuine network constraints that limit the ability, for example, for a unit to deliver primary frequency response because it is across a transmission line which is constrained, or it could be even tripped off, then this is really never captured in an SFR model. Also, there's only one frequency in the system, so we basically take the average frequency, which, for all intents and purposes, is like the center of inertia frequency. And for a small mesh system, this is actually a pretty good assumption. So something like the Swiss is a very good assumption. We assume that all the voltages in the system are well regulated pre and post disturbances, so we don't have any voltage stability issues pre-disturbance or even post-disturbance. And typically we use sort of simplified dynamic models for the governors and the primary frequency response parts here. And there are some models that use more complicated models for primary frequency response, but generally SFR models tend to use some more simplistic or simplified streamlined dynamic models. The Anderson model from 1990 is probably one of the most famous early SFR models. It's probably no means the earliest. I've seen some internal documents from the utility in Western Australia from 1979 with an SFR model. And so people have been working on this for many years, but this model does have some attractive features. And so the structure of the model is as follows. The inertia block contains the load damping inbuilt in the block, and this is the PFR, which has got some droop feedback. So you have here the droop coefficient with the feedback from the frequency deviation. And the PFR itself, you can see, is modeled as a lead lag block. So you have some gain, and then you have a lead component and then a lag component. And that lead lag block is really describing the sort of behavior, or the primary frequency response behavior of steam reheat turbine governors, where there's a short burst of response early on, and then there's a slower burst, which is the lag component. There is no consideration of demand response. So here the transfer function GS is basically equal to 0. One of the attractive features of this model is that it has a closed form solution for the frequency deviation delta omega. And here is the closed form solution. I'm not going to go through it all, but it does solve, and you do not need a computer to actually calculate the solution numerically. Well, I guess one of the issues with this is sort of the estimation of all the different parameters, because everything's in per unit, so you have to do a lot of conversions to make this model work more practically. This model here is a simpler and more practical SFR model than the Anderson model. Everything's firstly in natural quantities, so megawatts and in hertz, and there are some other attractive features to this model that make it a bit more useful from a practical standpoint, or at least just from doing simulations. So I'll walk you through the model. So first of all, this is just the inertia block, and damping is excluded or external to that inertia block. And it's just an input into the active power deviation. The other thing to note is that the primary frequency response has no feedback to frequency, so it's literally just a generic active power injection. And what we're saying in this is it's just modeled as a first order lag block, so you have some quantity of PFR, and then you have a speed of response of that PFR. And this is sort of a useful formulation when we want to provision the amount of spinning reserve or PFR required in any given situation. And there's also no other consideration of demand response here, so GS, the transfer function, is 0. Like the Anderson model, this one has a closed form solution for the frequency deviation, and here is that formulation. And another more attractive feature as well is that it has an analytical closed form solution for the frequency nadir. So you can calculate the frequency nadir without having to calculate the frequency deviation, then taking the minimum of it. The simple SFR model that was described in the previous slide assumed that the PFR was a first order lag block. And in this slide, I just wanted to dig in a little bit deeper and try and tease out whether or not this assumption of an aggregate PFR is a reasonable fit for actual responses. So the time domain expression for the lag block is this: PFR 1 take E minus T on tap. And on this figure, we see a PFR equal to 100 and different speed of response parameter taus. So as you can see, as the speed of response parameter gets larger, the speed of response gets slower. And so we tested this against some actual contingency events with different generating fleet configurations, and overlaid the PFR approximation onto the actual measured fleet responses. And you can see here, for a slower fleet, where tau is equal to 2.8, it's not too bad. You have the inertial component here, and this is the fitted curve. And same goes for a slightly faster fleet, where tau is equal to 1.6. So in conclusion, we find that this approximation is not too bad when we're trying to fit to actual events. I've described a few simpler SFR models that have analytical closed form solutions, but the more complex SFR models out there include much more detailed representations of the PFR. So rather than just aggregating all of the PFR as a lead lag block or just a first order lag block, the more complex models separate all the PFI into separate units or groups of units, usually based by technology type, which is what the microcosm model does. And you can see here that they've separated out the steam turbines from the combined cycle gas turbines, from hydro, from open cycle gas turbines, and so forth. And so each of these separate models have their own parameters and possibly even deviations on the dynamic model themselves. So other even more complicated SFR models use full dynamic models for generators, providing PFR, as well as the demand response or load response that's tripped via under frequency relays. So this is something that they were doing in ESCOM. So they've got the full dynamic model in dig silent and just putting it all into a single bus. So these more complex SFR models generally don't have any analytical solutions and have to be solved numerically. Load relief or load damping is something we've spoken briefly about earlier, and it is a crucial element in the SFR model. And as I mentioned earlier, it reflects the natural sensitivity of demand or loads to changes or deviations in frequency. And again, the most common mechanism is the proportional relationship between frequency and power consumption in induction motors. So as frequency goes down, induction motors tend to reduce their power output. So the total load in a system tends to decrease whenever frequency decreases, and vice versa. And the normal formulation for load relief in SFR models is as follows. So you have some kind of initial load, and you have a damping factor or load relief factor multiplied by the change in frequency. This is formulated in terms of megawatts, but you can easily reformulate this in per unit. And visually, this is what it looks like. As frequency falls, you get a corresponding decrease in load, and it's proportional. Now we want to talk about how we estimate the load relief factor D. Some early estimates of the load frequency characteristics were done by conducting live tests on the system. So this is something we discussed earlier in the conversation about the early SFR models, where when they calculated the power frequency characteristic, they actually intentionally tripped generators and transmission lines. So that study from the 1950s applies here, and as does the Berg study from Norway in the 1970s. There was also a study in the 90s by Sullivan and O'Malley, where they also tripped some generators with only one unit for primary frequency control running, and tried to estimate the amount of load relief and load response in the system. However, since then, the approach has sort of evolved into taking sample measurements of frequency and aggregate system load from the SCADA system after a contingency. So this is sort of the approach taken by PMI in the Great Britain system. And because load relief is modeled as a sort of linear proportional function of frequency, then the load relief factor can be estimated by a linear regression. So here are the steps. We take samples of frequency versus load, and then we plot those samples on the scatter plot, and we take a linear regression, and that the slope of that curve is D, the load relief factor. If only it were that easy. So the problem is that the aggregate system load is actually not directly measurable, but is normally a composite sum of all the generation in the system, so that it's so-called as generated values. So this leads to a number of problems with the standard estimation approach. The first one is that SCADA measurements are pretty low sample resolution. So it's 4 seconds in the Swiss, and they're generally not really very time synchronized, and they're subject to the effects of time averaging as generators are spread out across large geographic areas. One of the main issues as well is that the polling rate of different generators is different. So some generators are polled every 4 seconds and they'll give you a very accurate reading every 4 seconds. Other generators will give you a reading every 30 seconds or every minute. So the as generated values are actually not very accurate at sub 4 seconds or sub 1 second even resolutions. And yet that's really what we want when we are looking at a frequency disturbance. We really need sub second or even at least 1 second readings of load against frequency, because the disturbance is all over by the first 10-15 seconds. Another issue you'll find is that the measurement of as generated values is actually a measurement of electrical output. So it's not really equivalent to mechanical output under transient conditions. So the load didn't just go up a couple hundred megawatts during the event. If anything, it actually went down. So this spurious transient here is due to high rock-offs and the speed voltage terms in the synchronous machine state of flux equation causing the electrical power to increase, but the mechanical power has not. Also, the effects of load resource PFR, so things that are triggered by under frequency relays, actually needs to be removed from the system load trace, because that is not considered to be load relief, and that's actually considered to be PFR. So in conclusion, it's actually quite difficult to reliably select ordered pairs of frequency and load values during a disturbance. I mean, it's actually hard to find anything between here and then the nadir point. So most of the time it's subject to a lot of human subjectivity and inference. If there was high resolution measurement data available for the major generators or the PFR sources in the system, and this can be from fault recorders or PMUs, then there's an alternative method for estimating the aggregate system load rather than just taking readings from the SCADA trace. And that's basically to work backwards from the swing equation. So if you had all the PFR sources, all the traces, then you could get the aggregate change in PFR. You've got the trace for the tripped unit, so you can get the aggregate change in power change in the tripped unit. You have an estimate for inertia, and you have the sample by sample rock-off estimate, and you're basically filling in the blanks of the swing equation, and whatever's left over is your load. So this is an example from the Swiss. So this was a frequency trace after the contingency. This was the PFR during the contingency, and you can see here also that there was some load response. So this is a load resource that tripped off on under frequency relay, and here you can see the load trace after using this method. And what's clear here is that there's actually some spikes here, and the reason for this transient spike in the load is because we're actually including inertia in the PFR, and the swing equation, inertia is actually endogenous to the model. It's already built into this KE value, so strictly speaking, we should have removed that section. But in any case, you do get a better alignment between the frequency trace and the load traces for you to calculate the load relief factor. SFR models can be, and really should be, benchmarked against actual historical events to test that the model is valid. And here we have some examples of benchmarking exercises in the Nordic system. the SFR model was validated against some large historical disturbances between August 2015 and 2016, and these two exercises are shown below, and the simulated traces here are within 0.03 hertz of the actual frequency nadir, and that was what they were really benchmarking against. In the Swiss, the model that we used internally, it was benchmarked against a contingency event in May 2020, and you can see some pretty good alignment with the model that we have. The SFR models that we've discussed so far are fairly simple models, so it might be tempting to think that a more detailed model would provide more accurate results. So you might want to use a full network model that already exists for the transmission system, such as like a full PSSE model or a full Dixolent model with all the dynamic models of the generators and other reactive plant and wind turbines all built in. But some experience in some jurisdictions suggests that this is not necessarily true for frequency stability analysis. So consider this plot here from the Eastern Interconnection in the US, where the red line is a simulated frequency trace for a 4,500 megawatt generator contingency using the full model, and the blue line here is the measured trace. And you can see some real material divergences between the simulated and the measured traces. And the worst thing is that the simulated one is actually far more optimistic than what was actually measured, which was this lazy L frequency response curve. So the Eastern Interconnection Planning Collaborative, EIPC, created a frequency response task force in 2017, and part of the scope was to actually just improve the simulation models. And while progress has certainly been made, the latest EIPC progress report from October 2020 shows that they continue to encounter difficulties with aligning the base case model simulations with actual historical events. So here they've actually got two base cases, and they're trying to align an event from March 2019. You can see that there's some better alignment than before, but still not that good. John Undrell made some interesting observations regarding the use of full network models. Is that production-grade network models were historically developed to analyze transmission issues and are generally ill-suited for frequency control issues. And many of the dynamic models are largely based on assumption, the parameters, that is. There are many operating modes in the thermal plant, and they're chosen at the discretion of plant operators, and they're not accurately captured in standard network models. So the work goes on to say that dynamic models tend to be overly detailed with regard to the internal operation of power plant components, such as the turbines and the governors, but they're lacking in detail in the modes of operation that may be in effect. And we've seen this as well with coal-fired power plants in terms of their mill configurations, or combined cycle gas plants in terms of running steam bypass. Drawing from our own experiences in the Swiss, the following observations can also be made regarding the use of full network models. The dynamic models that we've seen are not really reflective of reality, and the PFR performance of the generating units in the full network model that we've seen are generally not tuned very well, and almost in all cases they're misaligned with measurements with actual events, and often very optimistic in terms of their PFR capability. The configuration of the study cases was also quite cumbersome. So if you're trying to set up a full model for an edge case or a future scenario where loads and dispatch have to be scaled, then configuring the full model requires real careful consideration of lots of parameters that are actually irrelevant to frequency stability. So looking at different load diversity or transformer tap settings and control and reactive plant settings, and most of them are not all that relevant to do this frequency stability analysis at hand. And finally, we found there was quite a lot of numerical sort of non-convergent errors and dynamic model of errors. And often this was due to the case configuration issues. So if you inappropriately scaled loads, if you didn't consider diversity properly, or you didn't set your reactive plant, you could have voltage stability and control issues. And so these are sort of issues that are not frequency stability related. And EIPC reported similar problems when they tried to scale up the EI model for a 10,000 megawatt benchmark simulation test. On the other hand, there are some examples of some successful uses of the full network models for frequency stability studies. So probably the most famous is the efforts that have been ongoing since the mid-90s by WEC on the west coast of the US in tuning and validating their models. And they're showing that the full network models can really accurately simulate system frequency response. So moreover, there's some evidence to suggest that all these network models can be tuned to yield some acceptable results. So from this study by Liu, they tuned the East Interconnection and the ERCOT base case models, and they just did a few adjustments. They're like including dead bands into governor models, adjusting the inertia values to be more aligned with the NERC values, and sort of tuning and governor non-responsive ratios based on sort of operational observations. And they were able to get some pretty good results from the full network models.